Now let me give you a slightly different case, okay? I said that this was a linear factor down the bottom here, okay? The denominator. What happens if there's more than one? What happens if it makes the degree of the bottom a bit higher? For instance, let's do this. This is example 1, example 2, okay? I'm going to keep that 3x minus 2 there. Okay. But suppose I have something a little more complicated. Okay. Now, without touching pen to paper, you tell me, why will this strategy over here not work? Why will it fail when it comes to this one down the bottom? What's the problem with it? Anyone confident enough to say it in an articulate way that I can hear? What is the difference, right? Degree 2, degree 1, okay? If the degrees are the same, it's very easy to do this step here, right? To get the numerator in terms of the denominator. But you try this with this and you're in trouble. You cannot get something degree 1 in terms of something in degree 2 without sticking some square roots in there and it turning out badly for you, okay? We'll get to the square roots later. So therefore, what are we going to have to do here? I'm going to teach you an important algebraic trick. Really, really cool, okay? It's called, and maybe you want to put this off on the side so we can revisit this question. It's called partial fractions. Okay, now just raise your hand if you've seen this before. Yeah, hands up. Okay, all right, let's give this a go. The idea of a partial fraction is to take this, and remember, we said the problem was this degree 2 down the bottom, okay? If we had degree 1, we'd be sweet, okay? But we can make it degree 1. Okay? Take this rational polynomial here, okay? We can rewrite this, okay, in such a way that you express it with those linear factors that we're after, which make things all nice and neat, okay? Because when you think about it, have a look at this right-hand side, okay? If you were to add these up together, what would you get, okay? Well, you've got these different factors here. You have to get a common denominator, right? That's how you add fractions. You would get this common denominator. But this is tons easier to work with, right? So if I can get it in this form rather than this one, I'll be sweet, okay? By the way, you will notice that is congruence, okay? This is going to be true for all values of x, not just some of them, okay? True and always true. How do I do it? Okay. Well, I want you to notice that. You can treat this kind of like a quadratic identity, right? Treat it like a quadratic identity. If I add these two together, okay, and get that common denominator, what will I get? What will the fraction be? It'll be ax minus 2, because I have to multiply that, and b x minus 1, right? That's my numerator. And of course, you get the common denominator that you were expecting, okay? But if these are equal, if these are always equal, and their denominators are the same, then the numerators must also be the same. Can you see that? See what's going on? So I can say 3x minus 2 will be equal to this. Whoops. Okay, now, remember, what was I trying to do? I introduced this a and b, these numbers. I probably should have said here. I introduced them as numbers, but I don't know what they are, okay? You're used to thinking of 2 variables, right? Or 3 variables. I'm going to need 2 equations to solve them, right? And it looks like you've only got 1. So what can I do here to help me? So it looks like there are 3 variables, right? It's not really, okay? These 2 constants here, I can leave them be. X, I can make whatever I like so long as it's convenient to me, okay? Make anything I like. So for instance, you could say let x equal to 2. That would be a convenient value. Why? It'll eliminate one of the constants, right? Which is the whole problem, okay? In fact, it'll eliminate 2 because it gets rid of x and it gets rid of a. So let's do that, right? What that leads to is, what's the left-hand side become? It'll be 6 minus 2, which is 4. That's equivalent to, actually, sorry, no, it's equal to. what do we say? This becomes 0, doesn't it? I might as well write that out so you see what's going on. That's the 0. Okay. Plus, how many lots of b am I going to have? 2 minus 1, which is just the 1, isn't it? Okay. So from this, I see b's 4. Okay, and you can pull exactly the same trick to get a. Let x equal 1. That's going to eliminate your b term. Let's do a bit of a shortcut here. 3 minus 2 is 1. That's going to be equal to 1 minus 2. So a is negative 1. Is that okay? See what I've done? So now coming back, if this is the case, I've got this up here. Negative 1 here and 4 there. Are you convinced? Should we just test it out, just to be sure? Because it seems a bit, especially this bit here, just like, let's make it whatever number we want. That's a bit hocus pocus. So just to make sure it works, okay, let's add them together, shall we? You'll get minus 1, x minus 2, 4 lots of x minus 1, all over the common denominator, which we've already predefined. Okay. What do you get up the top? Negative x plus 2, 4x minus 4. Does it work? Sorry, on the denominator. You bet it does, okay? So this technique, this partial fractions business, it's deceptively simple, isn't it? It's very simple. You're like, really? They saved us up to 4 unit to learn this? Well, it's only when you meet these kinds of problems that you need it, really, okay? So now, let's have a go at this problem, okay? I can rephrase it like so. Negative 1 on x minus, yep. Okay, that's it. And it's just 2 log functions, isn't it? You've got negative. Oh yeah, sorry. I just wrote it down wrong. Thank you. What's this? Plus 4. I suppose I should do this. Plus your constant. Okay.